Hey, so this is part 2 of the fall 2021 exam 3, where I'm going to go over the chiral, achiral, meso, and then the enantiomers, diastereomers. So this page. So the very first thing I guess you got to think of is that chiral. What does chiral mean? What does that even mean? It means that there is a carbon, a central carbon, that's connected to 4 different things. And it doesn't have to be 4 different atoms, because it could be connected to 2 carbons, but those carbons are connected to different things. So we'll see an example of that. Achiral does not have chiral centers. So achiral is going to have at least 2 atoms or groups that are identical. So for example, a carbon that's connected to, say, a bromine, a chlorine, and whatever, say 2 fluorines. 2 fluorines, and each of those aren't connected to anything different. It's achiral. It doesn't have any chiral centers. It's not connected to 4 different things. Meso is really a combination of the 2. It's like in the middle. So meso will have chiral centers, but it will also have symmetry, which I forgot to mention about with the achiral. So say that this is achiral. And so this is what you see is that this is not connected to 4 different things. It's only connected to 3 different things, because these fluorines are identical and they themselves aren't connected to anything else. So what you see though is that there's no chiral centers, but there is a plane of symmetry right here. So if you put this in the middle, this whole half would fold over on here. And even though you're like literally cutting these elements in the middle, it would still fold over, and you see that a fluorine would be exactly in the same place. So that makes it have a plane of symmetry. Meso, being a combo of the 2, will have a scenario where it is connected to 4 different things, and at the same time will have symmetry. So let's see if we have an example. What do we have here in this first one? So we got to label them as one of these 3. And it's only going to have an RS if it's chiral. So achiral is never going to have that. So what do we see? Let's focus on this one. Well, first of all, does it even have chiral centers? So does it have carbons connected to 4 different things? Let's look. This carbon. What is this carbon directly connected to? This carbon is directly connected to a carbon, right? A carbon, an oxygen, a hydrogen, and another carbon right here. This carbon is not connected to that hydrogen. The oxygen is connected to that hydrogen. So you gotta take that into consideration, or realize that. So this carbon is connected to a carbon, a hydrogen, oxygen, and a carbon. Is it 4 different things? Well, it sounds like no, because hydrogen and oxygen are different, and that's different than carbons, but it's connected to 2 carbons. But that's fine, because are these carbons connected to identical things? This carbon is connected to a hydrogen and oxygen. This carbon is connected to 2 hydrogens and another carbon. So that's different. So it is chiral. These are actually 4 different things, because that's essentially altogether it's connected to one thing, but those things are connected to different things. If this carbon was connected to, say that this was gone and this was the hydrogen and this was oxygen, then this carbon would also be connected to hydrogen, oxygen, just like how this carbon's hydrogen, oxygen. So then it would not be chiral. So this portion, it is chiral. So we have at least one. So it's definitely chiral or meso at this point, right? So we still haven't figured out. It's either chiral or meso. But let's look to see how many. What is this carbon connected to? This carbon's connected to a carbon, a hydrogen, and a carbon. Well, the hydrogens aren't connected to anything else, and that's the same thing, so it's not chiral right there. That's not a chiral center. All right. Now, let's look at the last one. This carbon is connected to a bromine, a hydrogen, and 2 carbons. This carbon's connected to 3 hydrogens. This carbon to 2 hydrogens and a carbon, so it's different. So it's chiral. So what I would do is point. So this is chiral, and then this is, which means there's going to be an R or S here, and nothing in the middle, because this carbon is not chiral because of that. All right, does it have a plane of symmetry? So can I cut it here, and this would fold on and look exactly the same? No, because if I cut it here, a bromine's going to fold on a hydrogen. That's not the same thing. And there too, and there also. So if I cut it here, do those fold and be the same thing? Only right there, but everything would have to. So no, there's no plane of symmetry, and there's chiral centers, so it's chiral. Now that we know that, we got to figure out if it's R or S. So looking only at the chiral centers, let's start with this one. What is this carbon again directly connected to? The one atom it is connected to is connected to a carbon, right? It's connected to an oxygen, a hydrogen, so I'm gonna put that hydrogen right here, an oxygen, and another carbon, right? So carbon, a hydrogen, an oxygen, and a carbon right here. So now we have to give each one of these elements a priority number, and hydrogen is always 4. It's always 4 because it always has the least priority. We're not going to be able to determine yet for these because they're the same, but it's based off of the number of protons and electrons. So for example, the bigger the number, when you look at the periodic table, the bigger the number above the element letter, the higher the priority is. So for example, hydrogen has a 1 above it because it only has 1 electron, 1 proton. So that means it's the lowest priority, so we give it 4, because 1, 2, 3, 4, so it's the lowest out of these. What is oxygen when you look at it? Oxygen is 8 on the periodic table. Carbon is 6, so oxygen is bigger, so it has bigger priority than carbons, so it definitely gets number 1. Number 1, number 4. So you know the biggest priority is going to be here for this carbon. The lowest one's going to be here, but I don't know if I'm going to go in this direction yet or this direction, but you're definitely going to start here because it has the number 1 highest priority. It's the heaviest element out of these ones. What do we have to compare? We have 2 carbons, right? So we have this carbon, and then say we have this carbon. What is this carbon connected to immediately? That carbon is connected to, you see it, hydrogen and an oxygen. And you don't look back down at the bottom like, oh, it's connected to, no, because we've already moved past that one. Now we're gonna show what only that is, not considering anything else. And remember, carbon always is connected to 4, has 4 connections somehow, because it wants and it needs 8 electrons total. So this carbon is connected to a hydrogen, right? And you see it's connected to an oxygen. And I have to consider this one for not with priority, figuring out priority, but I have to consider this one right now when I'm considering the fact that I need to figure out what this carbon is actually fully connected to. No, wait, I know it sounds confusing. So this carbon is right here. We see that it's connected to a hydrogen. I see it's connected to the other carbon. And what you see written is an oxygen, right? Okay. This is why I'm doing this, because you see CHO. Okay, CHO. Right, this C, the H, the O, and then this. Something's wrong. Something's off here, because that wouldn't even make sense. Carbon is always connected to 4 things. We're only seeing 3 things. That's because this CHO is actually the fact that this oxygen is double bonded. So this 4th thing is actually up here. So you see the carbon does now have, it's 4. 1, 2, 3, 4. Or you could think of 2, 4, 6, 8. Because that's what carbon always has in every situation. So you need to realize that this carbon is connected to this oxygen doubly through a double bond. And when you're figuring out priority, you have to actually consider this oxygen twice. So I'm going to say that this carbon is connected to an oxygen through a double bond, so I count the oxygens twice, and through a hydrogen. Right? Because you actually see that this carbon right here, it's already being considered. We already know what this is connected to. Now we're trying to figure out the priority between this, which is that, and this, which is that. So this is connected to this oxygen through double bond, then the hydrogen. All right. And then you have to look at this, because right, we have oxygen here as 1, hydrogen as 4, right? We're trying to see basically who's going to get the 2nd place, who's going to get the 3rd place. Is it this one or this one? Because then when we do the arrow, we're going to go in the direction of normal counting order. So it would be 1, 2, or 1, 2, depending. So what is this carbon connected to directly? Right, it has to be 4 things, so 1, 2, 3, 4, and it is. We basically already have this here, and that connection. So what are the other three? You see that it's actually two hydrogens, right? Hydrogen, hydrogen, and then this carbon. So we see, because we're only comparing this and this right now to figure out who's number two. So who's higher priority? A carbon connected to two oxygens and a hydrogen is definitely bigger and heavier than a carbon connected to only two of the lightest elements, hydrogen and a carbon. And carbon's lighter than oxygen. It's number 6 on the periodic table, whereas oxygen's 8. So this gets priority. So this will actually be number 2. And then this will be number 3. And it will be weird because you're not going to count 1, 2, 3, 4, right? You're going to basically always ignore and skip that one. You're always going to look to connect from 1, 2, 3. So we're actually going to go in this direction, right? Because oxygen had the highest priority, then this one got second place over this one because this was a double bond to two oxygens. So we go in this direction. Now what is it normally when we go in that direction? That's S normally, right? Because it's counterclockwise. If I was going this way to the right, like a right-hand turn, that would be R. It's going in clockwise, like 12 is here. It's like, oh, the minute hand, right? It's going in that direction. I think it's going in the right direction, the way that the clock goes correctly. And then S shows you the opposite. But with Fisher projections, right, these, like it's like a fish, it's like scales. That's how I think of like Fisher projections, like the fish thing. It's opposite. So it is here going this direction, but so this should be S, right? Should be S. But you always change it. You always flip it when it is a Fisher projection. So it's going to be R. The reason actually for this I had to look up is because Fisher projections are made specifically so that these things coming off of the sides are all wedges, which means they're all coming towards us. The way that they like distorted the molecule to show that all these things you put out to the sides are actually wedges coming towards us. But when they originally made the rules for determining if something's R or S, they specifically said that the hydrogen, like the lowest priority, and it's always the hydrogen, that needs to be going away from us. It needs to be dashes. So because Fisher projection makes it so everything is coming towards us, you have to flip it. So you could actually get the right thing if you flip this whole molecule and put the hydrogens here and the OH there, this there, and this there. That's actually the reason. So now we still got to figure out this one. So what is this carbon attached to? Because we know it's attached to 4 different things. We know that it is attached to a carbon. We know that it's attached to a bromine, a hydrogen, and another carbon. Well, remember, hydrogen's always going to get the least priority. You can already mark that. And bromine is pretty heavy. it is number 35 in the periodic table. So it definitely is going to get number 1. Now, again, and this is almost always what it is the situation, we have to determine between two of the same, elements, 2 carbons, we have to decide which one is going to get number 2 and which one's going to get number 3, so we know what direction to go into. Well, let me mark that. We know that the bromine is 1. So we're definitely going to start here. And we don't know if we're going like that or we're going like this. Well, what is this carbon attached to? That carbon is attached to 2 hydrogens and another carbon, right? Hydrogen, hydrogen, carbon. What is this carbon attached to? Only 3 hydrogens, right? Hydrogen, hydrogen, hydrogen. Well, so this one's 2 hydrogens of carbon. This one's only 3 hydrogens. Hydrogen's always the lightest, always the least priority, always the, not helping with anything. So it's going to be this one that gets priority. So that one's going to be number 2. And then this one will be number 3. So we're going to go in that direction. So again, remember, this is normally an R, but because it's Fisher projection, it has to be flipped. So it's actually an S. And a little trick thing that I saw and learned from a video I watched was that if you have CH3, because that's what it normally is, just here to show that, that H3 could be right here. That methyl group, with the hydrogen getting the number 4 always, this one always gets number 3, apparently. Always gets the next lowest priority because nothing is ever going to basically be as crappy as a carbon attached to 3 other hydrogens. So this one beat this one because it had one thing that was heavier. Nothing's going to be heavier or lighter than hydrogens. All right, so then the second one, what do we see? We see that we have a carbon here, right, and a carbon here, like always. What is this carbon attached to? That carbon is attached to a carbon, a chlorine, a hydrogen, and another carbon, which is actually this one down here, right? So again, we're going to know immediately hydrogen is going to get the lowest priority, but obviously you see I'm jumping because I need to figure out if this is even chiral. So let me back up. So this carbon, right? Chlorine, hydrogen, carbon, carbon. Okay, is it chiral? Only if these carbons are themselves attached to different things. This one, 3 hydrogens, this one, hydrogen, chlorine, and another carbon. So it's definitely different. So we are going to have to figure out RS. Now for this one, is it different? Let me just write it out also. Carbon. It's attached to, right, a carbon above it, then a chlorine to the left, hydrogen to the right, and then another carbon. But the carbons themselves are attached to different things, so it's also going to be chiral. So, is it chiral or is it meso? Well, if I split it, do I have symmetry? Here, if I split it right here and fold it over, it would be a chlorine fold over and a chlorine, a hydrogen, and a CH3 and a CH3. It definitely has plane of symmetry. That means it's meso. It's meso because it has at least 2 chiral centers, 2 carbons that are attached to 4 different things. And there's somewhere where you could fold it and the things would fall on top of each other and be the exact same thing. So the meso basically has what chiral has and what achiral has, because achiral only has symmetry. So now we have to figure out, again, is RS. So you could think, do you remember the trick? Hydrogen's always crappiest, always gets the lowest priority. I'm jumping again on that one. Then we know that, because right, we're only looking at one carbon at a time. And I already wrote all of this over here. So the hydrogen crappiest, chlorine the best because it's number 17. Carbon is number 6 on the periodic table, so it's definitely lighter. Now, what do we have? We have that this carbon is attached to 3 hydrogens, and then this carbon is attached to a chlorine, a hydrogen, and another carbon. So, right, remember I said if you see a CH3, it'll automatically get the third. The next lowest priority, we know this one's definitely 1, so this one is going to get 2. So that means we're going to move in that direction, which is counterclockwise, which should be an S. But Fisher projections, which this is, you flip it, it's not an S, it's going to be an R. Now let's do this last one here. All right, we know it's carbon connected to a carbon, a chlorine, a hydrogen, and a CH3. Again, quickly, then really jumping, you could see that one's definitely 4. We already know that one's going to be 1, and we know this, because it's CH3, it's going to get number 3. So then, right, we got 1, we got 4, we got 3, so this one would be 2, which is this one up here. So also be 2 for this side, so it's going to go like that. Because it's going counterclockwise, which should be an S, because it's not the right way, it's going to get flipped because Fisher projections are already flipped, so it's R. Hopefully that makes sense. I mean, it's ridiculous on a lot of levels, but whatever. So now these ones, the Enantiomers, the Diastereomers, blah, blah. So first of all, you got to think these are isomers, which means they're made up of the exact same elements and the same amount of those elements. So if you're looking at 2 compounds and they differ in one element, like, so there's one thing in one that's not in the other, they're definitely not isomers. So let's just look at this first one. What do we see? See, this is the same, this is the same, right? Both have hydrogens, they both have OHs, they both have BRs. So not only did they have literally everything the same, they also have everything in the exact same place, right? So it's like, oh, this COH, and then that H there, that C. So you see how everything is the exact same place? So they're not mirror images, right? Because a mirror image would be like you're looking, so this is you standing here, and you're looking in the mirror, and the mirror is right here. You should see the OH also right here. You should see the BR that you have on you, you should see in the mirror right here. And what's behind you should also looks like it's behind you in the mirror. It's not. This means it's the same exact compound. It's the same. Because you could literally take this and put it right on top of this, and everything's the exact same in the same place. Now let's look at the next one. We got CHO, CHO, CH3, CH3. We got OH, OH. We got hydrogen, 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 bromine, bromine. So they have the exact same elements and the same amount of them, like one bromine, like those two hydrogens, whatever. Everything's the same, so definitely isomers. Are they mirror images? So this is you again, right? You're standing. This is like in front of you on your shirt. This is like whatever, something behind you. Someone standing behind you. Think of, if you look in the mirror, you should see what's on you or in front of you as like the first thing in the mirror, right? And then like if this is standing behind you, it should be standing behind you in the mirror. So these are mirror images, right? They're mirroring each other. Mirror, 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 mirror. So when you have two things where it's all the same elements, they're just basically swapped or flipped, that is an enantiomer. Now let's look at the next one. We got COOH and we have CHO. All right, but we have hydrogen, hydrogen. We got 1, 2, 3 hydrogens, 1, 2, 3 hydrogens. We got a bromine, a bromine. We got OH and OH. We got Cl, Cl. We got the CH2, CH2, CH3, CH3. But we have COOH and we have CHO. We have one more oxygen than here. Remember, an isomer has to have the exact same elements, and they do have the same elements, they all have the exact same thing, but it doesn't have the same amount of them. This one has an extra oxygen, this one only has 1, this one has 2, so they're not isomers. So then we can't even like talk about these other terms because this is all isomers, just different kinds of isomers. So not isomers because they don't have the same amount of the same elements. All right, now the last one, what do we have? We have COOH, COOH, CH2, CH3, CH2, CH3. We have chlorine, chlorine. We have hydrogen, hydrogen, hydrogen. 3 hydrogens there. We got a bromine, chlorine, chlorine, fluorine, fluorine, hydrogen. Yeah, so we have the exact same things, right? Nothing in here isn't also in here. But clearly, right, what we see is that they kind of switched around. Are they mirror images? If it's a mirror image, the bromine would be right here because it would have to like be mirroring. That's mirroring, that's not, right? Because the chlorine should be here. So you see in these places, these ones aren't mirror images, but they do all have the same things. They're just jumbled a little differently. They're flipped. So they can't be enantiomers because the enantiomers are perfect mirror images and have all the same things. If they have all the same things, but they're just not mirror images, that's the diastereomer. So that's it for right there. Hopefully that helps.